So, good afternoon, everyone. Could you please press the thumbs up sign if you can hear me? Okay, so thank you very much. Good afternoon and welcome to the 5th webinar of the IMath Webinar series. I am Gino Angelo Velasco, the coordinator for research of the Institute of Mathematics. So before we continue, let me just remind everyone that this webinar is being recorded and it is being streamed live via YouTube. And the YouTube link is posted on our Institute of Mathematics official Facebook page. Okay, and so for questions later after each talk, you can type your questions in the chat box or you can feel free to unmute yourselves. Okay, so let us start. We'll have two speakers for this webinar. The first speaker is Dr. Romar de la Cruz. He is an associate professor of the Institute of Mathematics, and his talk is titled Minimal Code Words and Projective Geometry. So let us all welcome Dr. Romar de la Cruz.
Okay, good afternoon, everyone. Can you hear me?
Yes, sir, we can hear you.
Okay, so I will share my slides. Okay, can you see my slides?
Yes, we can see your slides. Thank you.
Okay, so good afternoon again, everyone. So sorry for the title. It's not the same as the one in the announcement, but you will see projective geometry later. So I'll be talking about minimal code words. So this is the outline of my talk. So first, I will give some theoretical background of the topic of my talk. I will give a survey of the known results on minimal code words. And then the third part is I will discuss the problem of finding the maximum and the minimum number of minimal code words. And then finally, I will discuss some recent results on the minimum number of minimal code words via geometric approach, so using projective geometry. Okay, so I will start by presenting some basic concepts in coding theory. So first, I will define a linear code. So an NK linear code C is a k-dimensional subspace of the vector space FQ to the n. So here FQ is the finite field of order Q. Now, what we call a generator matrix for a linear code C, so we denote it by a G. So this is a K by N matrix whose rows form basis of the linear code. Next, the dual code. This is the orthogonal complement of C. So the elements are the vectors X in FQ to the n that are orthogonal to every element of C. And then a generator matrix of the dual code, so it's also a linear code, is we call it the parity check matrix. Now, projective code, what we call projective code. So for a projective code, so the generator matrix has no zero columns and no two columns are linearly ended. So next, we define the support of a vector. So if you take a vector x, so the support of x is the, this is the set of positions where x of I is non-zero. So set of all I such that x of I is not equal to 0. So non-zero positions. And then we have the Hamming weight of a vector x. So it is the size of the support. Now the minimum weight of C is so the minimum of the Hamming weight of the among the non-zero code words of C. So we also have the Hamming distance between two vectors x and y. So this is the number of positions where the two vectors differ. And then we also have the minimum distance of C. So we take the minimum of the distances between any two distinct code words of C. Now for a linear code, the minimum distance is equal to the minimum weight. So now, what do we mean by a minimal code word? So first, when we say NKD sub Q linear code C, so this is a linear code of length and dimension K and minimum distance D. Now, this is what we mean by minimal code word. So we take a non-zero code word C. So we say it is minimal. So if there's no other non-zero code word C prime in C, such that the support of C prime is properly contained in the support of C. So minimal refers to the support. So with respect to, so minimal support with respect to set inclusion. Now, the main problem concerning minimal code words is given a linear code C, so we want to determine the set of minimal code words or the minimal supports of C. In general, this is a difficult problem, even computationally. So it's difficult to compute the set of minimal code words of a given linear code, especially if the code is very large. So here's a simple example, so a small example. So here we have a 422 binary linear code C, are the code words. So by inspection, we can see that the minimal code words are these two vectors, 1010 and 0101. And a non-minimal code word is the all one vector. Now, let us consider a special case. So a special case can be found in graphs. So if we have a connected graph with P vertices and Q edges, so we can construct some binary codes. So using the incidence matrix of the graph. So the incidence matrix is the matrix, so the rows are indexed by the edges, the columns are indexed by the vertices. So we take the incidence matrix and then we take its span over the binary field. So we obtain two binary codes. So one is called the bond space. So in graph theory, so it has parameters Q, P minus 1, so length Q, dimension P minus 1. The other one is the cycle space. So it's the dual of the bond space, and it has the following parameters. Now, for this two binary codes, so here are the minimal code words. So for the bond space, the minimal code words are the incidence vectors of the cut sets. So a cut set is a set of edges in a graph that if you remove them, so it makes the graph disconnected. And then for the cycle the actually are vectors of the cycles in the graph. So an interesting question here is how about for the codes generated by the adjacency matrix of the graph? So nothing is known about the minimal code words obtained from this matrix. So this is a special case of minimum. So in the setting of graphs. Now, a general setting for incidence vector is the so the row of an incidence matrix is so it's indexed by an edge, and then the columns are indexed by the the columns are indexed, the rows are indices. So the entry in the matrix if the vertex is in the edge, and then 0 otherwise. Okay, so now from a specific case, we general setting. So we go to metroids. Metroids are objects studied in combinatorics. So maybe some of you are familiar with this. So an example of a metroid is what we call vector metroids. So these are constructed based on the lineage columns over FQ. Meet over FQ. So you can define a metroid based on the linear dependence of the columns. So it follows that if you have a linear code C, so you take the generator matrix, so you can have a vector metroid. And then if you consider the minimal supports of the code words of C, so this correspond to the circuits, what we call the circuits in metroids. So this is the more general setting of minimal code words. So it is studied in the setting of metroids. Now, why do we study minimal code words? So here are some applications. So it was first studied in coding theory in relation to decoding linear code. So there were some algorithms for decoding that were introduced that uses the set of minimal code words. Now in cryptography, so two applications can be found in secret sharing schemes and in secure two-party computations. I'm more familiar with secret sharing schemes. So secret sharing schemes is a method of distributing access to a secret to a group of participants. So in such a way that only certain subsets of participants can access the secret. So there's one construction of secret sharing schemes that uses linear codes. So, and the significance of minimal code words is, so they are used to determine the access structure of the secret sharing scheme based on the linear code. So access structure is these are the set of subsets that can recover the secret. So here are some applications of minimal code words. Okay, so next I will give some known results on the theory of minimal code words. So first, some general properties. So these were given in these three papers. So let C be an NKD linear code over FQ, and then we consider a parity check matrix for C. So if we take a code word C and we denote its support by U, so the support is the set of non-zero positions. So the support is minimal if and only if the rank of this matrix H of U. So H of U is we just take the columns of H indexed by the elements of U. So it's a subset of the columns of H. So we can determine if U is minimal if the rank is equal to this, so size of U minus 1. And then if U is minimal, so the size of U has an upper bound, so it's at most n minus k plus 1. And then if the size of U is not large enough, so it is minimal. Another interesting property is the following. So if you take the set of minimal code words, so they form a spanning set of the linear code. And then for binary codes, so if C is non-minimal, then you can decompose C. So as a sum of two code words, X and Y, with disjoint supports. So these are some of the general properties known for minimal code words. Now, so next, I will present a general method to determine the set of minimal code words. So basically, this is an exhaustive search. So given again a linear code C, so based on one of the properties in the previous slide, so if the weight of C is less than or equal to 2D minus 1, so if the weight is small enough, it is minimal. And then another property is if the weight is greater than or equal to n minus k plus 2, then it's not minimal. So we only need to check the following weights. So between 2D and n minus k plus 1. So for each of the code words whose weight is between 2D and n minus k plus 1, so we can apply the parity check matrix test, the first property that I mentioned. So up to now, this is the only algorithm to determine the set of minimal code words. So there were some improvements, so you can use some special properties of the code, so automorphisms. So for example, if it is cyclic, so you can exploit that to determine. But in general, it's still exhaustive search. So you have to check basically each code word to see if it's minimal or not. So it's an open problem if this can be improved. Okay, so now we go to the maximum and the minimum number of minimal code words. So since it's in general very difficult to determine the set of minimal code words, so we try to look at the maximum number and the minimum number of minimal code words. So when we count the number of minimal code words, so basically we only focus on the non-equivalent minimal code words, so the linearly independent ones, because if we take a minimal code word, or if you take a non-zero code word, if you multiply it by a non-zero scalar, so you get another code word with the same support. So when counting the minimal code words, so we only count the non-equivalent, or basically we just count the minimal supports. So we denote it by M of C. So for the maximum, So first we define the following. We let C sub Q of NK be the set of all projective NK linear codes. And then we define this quantity M sub Q of NK. So this is the maximum M of C. So M of C is the number of non-equivalent minimal code words. So for NK PC. So far, these are the upper bounds for this quantity. So the first upper bound, so it is less than or equal to n taken k minus 1. So this was proved actually in the setting of matroids. So this upper bound. Now the next two, actually this was proved in the setting of linear codes. So one was by Agrell, and then the other one is this recursive upper bound. Now, lower bounds on the maximum number are the following. So the first one actually is a random coding bound. So meaning you take a random code, so you can estimate that the minimal code words so satisfies the following lower bound. Now the second one, so this take note, these lower bounds were only proved for binary codes, so M sub 2. Now for the second one, so you have summation I from 1 to this quantity, floor of n over d of nk. D of nk here is the so for nk codes, you take the largest value, possible value of the minimum distance. And then you compute this, so this will be greater than or equal to 2 to the k minus 1. But in general, this is not a good lower bound. Okay, so how about for the minimum? So similar to the maximum, so we define this quantity small m sub q of nk. So this is the minimum of M of C for all NK codes C. So this is what we know so far for the minimum. So lower bounds. So it is at least K. So again, proved in the setting of matroids. And then we also have these two lower bounds. Now, so far, the best lower bound is the third one. So M of C is greater than or equal to N. So it is at least the length. But this one is proved in geometry. So it's not proved using coding theory. Okay, so now I will present some results on the minimum number of minimal code words. So using a geometric approach. So this is joint work with the following three mathematicians from University of Bayreuth. So Michael Kiermaier, Sasha Kurst, and Alfred Basserman. So we are going to use the projective space. So I use the following notation for the projective space. So PG of FQ to the K. So one way to represent projective space is using this the vector space. So FQ to the K. So in this projective space, the points are the one-dimensional subspaces of FQ to the K. And then the lines are the two-dimensional subspaces. Now the hyperplanes are the K minus 1 dimensional subspaces of FQ to the K. Now we are also going to use the following quantity. So the Gaussian coefficient. So it's this one, q to the k minus 1 over q minus 1. So it gives the number of points and also the number of hyperplanes in the projective space. So how do we connect the linear codes and projective spaces? So we recall the generator matrix. So if we have an nk code C and then take a generator matrix. So a generator matrix is the k by n matrix whose rows form a basis of the linear. So we consider the columns of the generator matrix. So we denote the ith column by sub I. You can view as one-dimensional subspaces. So we can view the columns as points in the projective space. So if we have a linear code C, so we take a generator matrix, so we can associate a multi-set of points, okay? So it's a multi-set of points in the projective space on fq to the k. So the points are the span of each column. So we treat them as one-dimensional subspaces. So it's not it's a multi-set. It's not necessarily a set. And then take note that we only consider projective codes. So we will restrict to projective codes. So what will happen is this multi-set will become a set. So that's how we associate a linear code with a set of points in the projective space. Now, if we take a non-zero code word C, so C is equal to U times G. So G is a generator matrix. So where U is a vector in F to the K. Now, if we consider the hyperplane, this one, the orthogonal complement of the vector. So we can see that each zero code word corresponds to a hyperplane. Now, in addition, so a code word corresponds to a hyperplane. Now, if we look at the weight of the code word, the support of the code word, so we have the following. C sub I is 0 if and only if the ith column of the generator matrix is in the hyperplane. So it follows that the weight of C is equal to this. So the cardinality of P, so the set corresponding to the linear code, minus the cardinality of the intersection of P and the hyperplane corresponding to the code. Now, we take note that two linearly dependent or equivalent code words correspond to the same hyperplane. And then I already mentioned this one. So if C is a projective code, so the columns of the generator matrix, so no zero column, and then no two columns are linearly dependent. So the set of points in the projective space associated with the code becomes a set. Now, this is not new. This association between codes and projective points, it's not new. So it was used before in the search of optimal codes. So there's nothing new here. So now we look at the geometric characterization of minimal code words. So we recall that a code word is minimal. So if its support is minimal, so with respect to set inclusion. So when it's not minimal, so it follows that there exists a non-zero code word C prime such that this is satisfied. So actually P intersection H sub C, this is the set of zeros. So the set of zeros of C is properly contained in the set of zeros of C prime. And we have followed the following characterization of minimal words. A non-zero word C is minimal if and only if so the span of the set of zeros of C, so this is the set of zeros, so P intersection with the hyperplane associated with C, so the span of the points is H sub C, the hyperplane, so it spans the hyperplane. Equivalently, the dimension of the span is -1. Now, using this characterization, so we can already say the following. So first, if C is minimal, and we know that the weight of C is equal to this n minus the cardinality of the intersection of P and H sub C. And then by this lemma, so if it's minimal, the dimension span is k minus 1. So it follows that the weight of C must be at most n minus k plus 1 because this quantity here, the set of zeros, so it must have at least k minus 1 elements. So this will be less than or equal to n minus k plus 1. And then we also have the following. So so m sub q, small m sub q is the minimum number of minimal code words among the nk linear codes. So we can determine the following. So if the length is equal to this, so this is the Gaussian coefficient. So the number of points or the number of hyperplanes. So the minimum is equal to this. So basically you take all the points in the projective space. And then this one also follows. So if we increase the length, so it's all the minimum number of minimal code words will also increase. And then for the maximum, so this also follows from the lemma. So the maximum value will be n taken k minus 1. But these three are already known, but I just mentioned that they follow from the geometric characterization of minimal code words. So now let's derive a lower bound on the number of non-equivalent minimal code words of C. So using the characterization, so if C is a non-minimal code word, so it follows that the span of P intersection H sub C, so it will be a subspace of the hyperplane H sub C. So we have a subspace U sub C such that the span is a subspace of U sub C. So this implies that so P and its intersection with this set, so H sub C minus U sub C, so you take away U sub C. So they will have an empty intersection. Now, this gives a restriction on the possible length of the code, if it has a non-minimal code word. So recall that the length is the size of P. So this condition gives a restriction on the possible length of a linear code C with a non-minimum code word. And so we define the following quantity. So we denote it by alpha sub q of kr. So this is the minimum cardinality of a set S, set of points in the projective space such that it satisfies the following two conditions. So there exists R different hyperplanes, H1 up to H sub R, and R subspaces. So U sub to U sub R of codimension 2 or dimension k minus 2. So with U sub I, a subspace of H sub I, and then we consider the following. So H sub I minus U sub I. So you take the union, I from 1 to R. So it's containing S. So we take the minimum cardinality of a set satisfying this condition. Now, for some specific values of K and R, so if K is 2, so we have the projective space based on F squared. So basically what you have are just the points. You only have points. So it follows that alpha q of 2R is R. And then if R is 0, so is alpha sub q of k is 0 is 0. Now, the significance of the quantity alpha is given in this proposition. So it gives a lower bound on the number of non-equivalent minimal code words. So let C be a projective NK code, and then R an integer satisfying this condition. So if the length n of the code is greater than this quantity, or here you have the Gaussian coefficient, so the number of points in the projective space, so minus alpha sub q of kr, then it follows that the number of minimal code words will be greater than this quantity. So the number of points minus R. So here's an outline of the proof. So first, we already know this upper bound on the number of minimal code words. So it's at most the points or the number of hyperplanes. So now, if M of C is less than or equal to this one, so number of hyperplanes minus R, so it follows that at least are non-minimal code words. And as at least are non-minimal code words, so using the characterization for the minimal code words, non-minimal code words, so we have the following. So each non-minimal code word corresponds to a hyperplane that has a subspace U sub I of so satisfying this condition. So P intersection with this union is equal. So this will imply that the length n, which is the cardinality of P. So it will be at most the number of points or the number of hyperplanes minus alpha sub q of kr. So now, based on the previous proposition, so it's important to determine the values of alpha sub q of kr. Okay, so we were able to determine the values for small values of r. So starting with r equals 1, so by direct counting, this is q to the k minus 2. So you only have one hyperplane and one space of codimension. And then for r equals 2 and k greater than or equal to 3, so we obtain the following. Alpha sub q of k2 is q k minus 2 minus q to the k minus 3. Before I continue, how much time do I have left?
Well, no problem. Just continue, Dr. Del Cruz. I think we have.
Okay.
There are only a few slides left. Or no worries.
Okay. This obtained by a direct counting. So here you have two, since R is 2, you have two hyperplanes. So you count the possible size for S, and you obtain the following. And then for R greater than or equal to 3 and K greater than or equal to 3, we obtain the following. So alpha sub q of KR is equal to this quantity. So R times q to the k minus 2 minus R taken 2 times q to the k minus 3. So if q is odd and R is less than or equal to q, or if q is even and R is less than or equal to q plus 1. So you can see from the conditions that R must not be large enough. So the outline of the proof is, the idea for the proof is the following. So first, you can obtain the following lower bound. So by direct counting also. So the next part is I construct a dual arc. So this is a set of points with certain properties in space. So fq to the 3. So you can show that equality is obtained. So for example, for k equals 3, r equals 3. So this is an illustration of a dual arc. So a dual arc is a set of lines, no two which have no three of which have the same have a common point. So for k equals 3, r equals 3. This is an illustration. The lines H2A, so bases u sub i's are the points. So here by counting, you can obtain alpha sub q of 3 is equal to 3q minus 3. So now we apply the lower bound that we obtained to compute some exact values for the minimum number of minimal code words given the length n and the dimension k. So basically we have the following. We have the following condition for r and then for n. So n must be greater than this quantity and less than or equal to this quantity. So it will follow that the minimum is equal to this. So basically this follows from the lower bound. Okay, now as a corollary, so we also obtain the following. So for k greater than or equal to 2, we have m sub q of nk is equal to this. So the number of points or the number of hyperplanes, if and only if the length is in this range. So as you can see, the number of minimal code words is equal to the number of hyperplanes. So it means that all the non-zero code words are minimal for codes with whose parameters are in this range. So this follows from the proposition. And then for k greater than or equal to 3, so we also have the following. So the m sub q of nk is so number of hyperplanes minus 1 So if and only if the length is in this range. So here I present a table on n sub 2 of nk. So we were only able to compute for the binary case, because in general it's difficult to compute for this one. So here's a table for small values of n and k. So we apply the results to determine some of the values here. For the other values, so it was done by an exhaustive search. Okay, so some concluding remarks. So the geometric approach can be extended to subcodes. So you can view a code word, a non-zero code word, as a one-dimensional subcode. So you can consider higher dimensional subcodes. So they also have, we can also define the support of subcodes. So there's a nice natural extension of the geometric approach to the support, to subcodes with minimal support. And then, so immediate open problems are the following. So determine the value of alpha sub q of kr for the values of k and r not covered in the results. And then another immediate problem is to apply the geometric approach to study the maximum number of minimal code words. So if you notice, we only obtain results on the minimum. So, okay, so for those interested with secret sharing and linear codes, so I mentioned one of the application is on secret sharing scheme. I'd just like to promote our book. So I think this will be available next year. So talks about secret sharing schemes and linear codes. So there's some chapters here on minimal code words. So that's the end of my talk. Thank you very much.
Okay, thank you very much, Dr. De La Cruz. Let us go. I'll give him a warm round of virtual applause. Okay, so thank you and congratulations on the book.
Thank you.
Okay, so the floor is now open for questions. So you can raise your hand or you can directly unmute yourselves. If you have any question, do we have any question from the audience?
I think Carmen has a question earlier, but I'm not sure if I answered it.
Carmen?
Good afternoon din. Nagpa-clarify lang ako kung ano yung incidence vector kasi yun. I think na-explain ni Romer yung incidence matrix.
Yeah. Okay, I mean, na-clarify ko ba yung incidence vector?
So yung incidence vector, paano siya kinukuha sa incidence matrix? Row ng incidence matrix, yun ba yun? Or kukunin mo yung nagko-correspond doon sa subgraph, doon sa cycle or sa whatever?
Well, siguro general way to define yung incidence vector. So it refers to, parang kuha ka ng subgraph. Okay, I'm thinking kung paano siya ma-define ng mas maayos. Pero yung row kasi nung, kasi I mentioned incidence vector nung nung cycle sa cut sets. No? So I think you're referring to that. Pag kinuha mo yung rows kasi ng incidence matrix, pag kinuha mo yung nila, yung symmetric difference. So makukuha mo yung incidence vector ng graphs, ng subgraphs ng graph. I'm not sure kung malinaw yung pagkakasabi. Malinaw ba, Carmen?
Yeah, I think Carmen, nag-okay si Carmen.
Basahin ko na lang sa paper. Baka nga, makita mo siyang e-mental eh. So baka kailangan ko lang makakita ng example.
Yes,
But
so maybe.
I think Carmen, kasi yung code words, yung code words kasi yung positions, 'di ba, indexed by the edges. 'Di ba, yung positions mo indexed by the edges. So pag meron kang subgraph, so ang value nun 1 kung nandun yung edge na yun sa subgraph na yun, 0 kung wala. Yun yung magiging linear combination ng yung rows ng incidence matrix. Ganun yung mangyayari dun sa.
Okay.
Okay, thank you. I think we have one more question. Dr. Valdez raised her hand earlier.
Yes, thank you. Salamat for the very clear and informative presentation on minimal code words. I have a few questions. Una, yung nabanggit mo nga kanina yung you can consider the linear code associated with the incidence matrix, and then you can apply certain techniques to determine the minimal code words. And then you also mentioned that the study can be or may be extended to adjacency matrices. Pero sabi mo, tama ba yung understanding ko? Open problem pa ito in general?
Oh, open problem pa yun. Actually, sinusubukan ko yun, pero so far, may mga results kaming nakuha. Pero walang hindi kasing, it's not as nice as, as compared to yung codes from incidence matrix, wherein you can describe as incidence vectors ng cut sets, incidence vectors ng cycles. Hindi kasing ganda nun sa adjacency matrix.
Okay. But meron na bang mga known results for, let's say, certain family of graphs?
Yung adjacency.
Using adjacency matrices.
Meron. Hindi ko lala kung na-publish na yan. May isang paper on that.
Okay. Tapos, yung isa, kasi binibilang yung, kinukuha yung maximum and minimum number of minimal code words, ano? Anong significance ng maximum or minimum numbers? For example, diba sa secret sharing scheme, meron ba siyang significance? Bakit
well, theoretically, ano yun parang common problem sa combinatorics, di ba? Or sa graph theory, yung extreme cases. So, halimbawa sa graphs, pinag-aaralan yung maximum number of cycles, minimum number of cycles. So, ganun din yung sa matroids. So, ang ginawa namin, we look at it in the setting of linear code. So, in between siya. Pero, application-wise, sa decoding, yung decoding application, ang requirement doon yung codes with very few minimal code words. So yung minimum yung ginagamit doon.
Okay.
Sa secret sharing naman, sa secret sharing kasi pinakamahalaga yung ma-determine mo talaga yung minimal code words. Pero if you have information on the maximum or minimum, somehow madi-describe mo pa rin yung access structure ng secret sharing scheme.
Okay, last na yung nabanggit mo kanina, doon sa dulo yung concluding remarks na parang pwedeng gamitin yung geometric approach on determining the maximum number of minimal code words na open problem pa. Tama ba yung aking? So ano na yung status ng doon?
Wala. So far wala. Open yun. Hindi namin mahanapan ng pwedeng. May results kami sa maximum pero iba yung ginamit namin. Hindi yung geometric approach. Hindi namin mahanapan ng application yung geometric approach. So far sa maximum.
Okay, yun lang. Congratulations pala sa book.
Thank you.
Okay, yun lang. Thank you.
Okay, so thank you very much. So
Si
again,
Weng yata may question. Yung
Weng?
code automorphism. When you were asking about code automorphism, tama ba? Example when I'll answer it by a specific example, yung kapag cyclic. So, pag cyclic kasi, di ba, if you take a minimal code word, pag in-apply mo yung cyclic, di ba, na permutation, you obtain another minimal code word. So, kumbaga nakakaroon ng nag-group mo yung mga minimal code words sa isang linear code kapag cyclic siya. Or in general kapag may code automorphism. So kumbaga yung search mo for the minimal code words, so somehow nare-reduce yung complexity ng search. Kasi mag-group mo yung code words using yung code automorphism. So kaya nare-reduce yung complexity. Pero in general, pa rin siya? Computationally difficult pa rin yung pag-search.
So maybe the other questions you can send Dr. De La Cruz an email. Okay, so I think his email is on the IMath webpage. So again, let us thank Dr. Romer De La Cruz for giving that very nice talk. And let us all give him again a warm round of virtual applause. Thank you.
Thank you. Thank you for the question.
Okay, so at this point, we will have a 3-minute break. So maybe let us go back at 2:02 p.m. for the next talk by 3:02, sorry, by Mr. Homer De La Cruz. Good afternoon and welcome back. I hope everyone's back. Okay. So let us now proceed to our next speaker. Our next speaker is Mr. Homer Franz C. De Vera. So he is an instructor from the Institute of Mathematics, and his talk is titled Quotient Complete Arc-Transitive Latin Square Graphs Associated with a General Semilinear Group of Degree 1. This is joint work with Dr. Maria Carmen D. Amara. So let us all welcome Mr. Homer De Vera.
Hello po.
Afternoon,
Okay lang
sir.
po ba yung audio?
Yes, we can hear
And
you
nakikita
clearly.
po yung
Yes,
slides. Okay.
yes,
Thank
kita.
you. Sige po. Good afternoon, everyone. My name is Homer, and I will be presenting our work together with Dr. Carmen Amara, entitled Quotient Complete Arc-Transitive Latin Square Graphs Associated with the General Semilinear Group of Degree 1. So our study is under the field of graph theory, where we study graphs, which are basically set of nodes connected by channels. In math, graphs are the abstraction of interconnection networks, which in real life could vary from biological to technological networks, etc. So symmetric graphs in particular are graphs which possess some degree of self-similarity and are associated with a group of symmetries. These graphs have been studied extensively and have various applications. For a given symmetry property, a common type of problem in graph theory is to describe all graphs and corresponding groups which has the said property. So in our work, we looked at Latin square graphs which have certain properties to be called quotient complete and arc-transitive. So some preliminaries on permutation groups. Suppose we have a non-empty set omega and a group G acting on omega. We use exponential notation omega raised to G. An orbit of omega is the set of all images of omega under the action of elements in G. And we say that G, or the action of G, is transitive if there is only one orbit in the set omega. We say that a partition P of omega, of the set omega, is G invariant if every element of the partition, which are subsets of the set omega, under the action of G remains an element of P. And given a normal subgroup N of G, an example of a G invariant partition is the set of N orbits. Now let us formally define graphs. Let V be a non-empty set. A simple undirected graph, or simply a graph, gamma, is composed of the set of vertices V and the set of edges E, where edges are two-element subsets of V. Say we have an edge UV. We also say that U is adjacent to V and vice versa. Also that the ordered pairs UV and VU are arcs. So here are some easy example of graphs. A complete graph has an edge set that contains all possible pairs of vertices, and an empty graph is a graph with no edges. An automorphism of a graph gamma is a permutation of the vertex set that preserves the edge set. For a subgroup of automorphisms G, we say that gamma is G vertex transitive if G is transitive on the vertex set, and gamma is G arc transitive if G is transitive on the arc set. An important type of graph that we will be dealing with are the Cayley graphs. So given a group G and a non-empty subset S of non-identity elements, which contains their inverses, the Cayley graph of G with respect to S is the graph with vertex set G, and edges are the pairs G and S times G. The Cayley graph of G with respect to S is G vertex transitive, and it is G arc transitive if and only if S is an orbit of the point stabilizer of the identity element in G. And now recall that given a normal subgroup N of G, the set of n orbits form a G invariant partition. Hence, we can form the normal quotient graph gamma n, the graph with the n orbits as the vertices, and the edges are pairs of n orbits, such that there exist elements in each respective orbit which are adjacent or which form an edge in gamma. So some remarks on normal quotients. Normal quotient graph gamma n is non-trivial or not that trivial graph, which is the graph with a single vertex, and if n is intransitive. And it is proper if n is not the trivial subgroup. So normal quotient graphs are known to inherit some of the properties of the original graph, including vertex and arc transitivity. Normal quotient reduction is what we call the method used to analyze certain families of graphs by taking normal quotients. So in a series of studies by Drs. Amara, Judici, and Prager, the family of arc-transitive diameter 2 graphs are analyzed. And the following is the key theorem. For any gamma G in the family G arc-transitive, there exists a normal quotient gamma n such that either all subsequent normal quotient of gamma n is trivial or gamma n is quotient complete, which means that it has at least one non-trivial complete normal quotient, and each of its other proper non-trivial quotients is either complete or empty. So to contribute in the analysis of the mentioned family of graphs, we study those which are quotient complete, more specifically quotient complete Latin square graphs. So let's just discuss quickly what are Latin square graphs. A Latin square of size n is an n by n array of n distinct symbols appearing once on each row and once on each column. The Latin square graph is the graph whose vertices are the cells of the Latin square expressed as ordered triples, row, column, and symbol. And edges are pairs of triples which agree in one position. Note that the Cayley table of a finite group is an example of a Latin square. So as an example, here is the Cayley table of the elementary abelian group, C3. Hence, we can represent the Latin square graph of C3 by this figure. For simplicity, we drew this figure this way. Please note that all vertices connected by a straight line or diagonals in an arc are adjacent to each other. For example, a 0, 0, 0, 0, 0, and 0, 2, 2 form an edge, as well as a 0, 0, 0, and 2, 0, 2, and 0, 0, 0, and this one, 2, 1, 0. So we drew the graph this way just for simplicity. So what are quotient complete and transitive Latin square graphs like? In a 2018 paper by Dr. Amara, detailed constructions are given. If the Latin square graph gamma is G quotient complete and G arc transitive, then gamma is isomorphic to a Cayley graph of a vector space V with respect to a subset S, where V is the direct sum U plus U, whose elements are written as ordered pairs, and U is a vector space of dimension V over the finite field. S is precisely the neighbors of the zero vector. G is this semi-direct product of the group of translations of V, and G0 is a subgroup of the direct product of the general linear group of U and S3, where the projection of G0 onto G of U is H. Okay, so while detailed constructions for such graphs are given in the 2018 paper, our goal in this study is to provide an explicit list of groups G, those especially associated with the general semilinear group of degree 1. A note that H mentioned here is a finite linear group which is transitive on the non-zero vectors. All such subgroups are known and have been classified by C. Herring. Subgroups of the general semilinear group of degree 1, gamma L1 P to the D, form a family of those. So to describe gamma L1, this is defined to be the semi-direct product of GL1Q and its automorphism of the finite field with P to the D elements. This is generated by omega, which is the primitive element, and tau, which is the Frobenius automorphism. And this is the action of an element in gamma L1 P to D to an element of the finite field. So by a result from D. Folser in his 1964 and 1978 papers, every subgroup of gamma L1 P to the D has a unique representation. If X is a subgroup, then there exist unique integers C, E, and S, such that X is the subgroup generated by omega C and omega E tau S. And CES satisfies these conditions, capital F1, F2, and F3. We say that X is in standard form and CES are standard parameters of X. So moreover, X is transitive if and only if either C equals 1. So from F3, if C is 1, then E equals 0. Or both F4 and F5 are satisfied. So it follows that the transitive subgroups are those generated by omega tau S for any divisor S of D, and subgroups generated by omega C and omega E tau S, where the standard parameter CES satisfy the following. So F1 is modified to F1 prime since we separated the case when C equals 1 to this first form. So observe that it is not that easy to compute values for CES satisfying these conditions in order to get an explicit list of transitive subgroups of gamma L1 P to D. Thus, we try to find equivalent conditions which are easier to apply. So proposition 3 is one of our results. So the transitive subgroups are the following: subgroups generated by omega and tau S for any divisor S of D, and generated by omega C, omega E tau S, where CS satisfy the following set of conditions, small letters F1, F2 to F5. So in our proof for this proposition, it remains to show that CES satisfy capital, excuse me, it remains to show that the standard parameter CES satisfy capital F1 prime to F5 if and only if they satisfy small letters F1 to F5. So we present a portion of the proof, assume C greater than 1. In our proof, we use mostly elementary number theory. To show necessity, we assume conditions capital F1 prime to F5 are satisfied, and we show conditions small f2 to F5. For condition small f2, we show that CS divides D. Conditions capital F3 and F4, here written below, imply that C divides the GCD of these two numbers, which is then equal to this expression here on the right. Therefore, by condition capital F5, since C does not divide this expression here for any C prime between 1 and C, the GCD of D over S and C cannot be less than C, okay, given that C divides this number. Hence, a GCD of D over S and C is at least C, implying that the GCD is equal to C. Thus, C divides D over S, i.e. CS divides D. Excuse me lang ba? So let's continue with the proof. For small f3, we need to show that E is between 0 and C, and C and E are relatively prime. Suppose for a contradiction that the GCD of C and E is greater than 1, and let C prime be this number C divided by their GCD, hence C prime is less than C. We claim that C prime divides this expression, which would then imply that since C prime is C divided by the GCD, C divides E times this, which is a contradiction by F5 since C prime is less than C. Therefore, GCD of C and E is equal to 1. And to show this claim, our method is to show that each prime divisor R of C divided by GCD of C and E divides e to the S minus 1. And we use this useful trick for prime R and positive integer I. We can find the largest power of R dividing this expression, which is a known formula. Of the proof of necessity showing condition small f4 to f5 uses similar arguments. So now let's assume small f2 to small f5 are satisfied. What's left is to show the capital F1 prime to F5 is satisfied. Capital F2 immediately follows from small f2. And for the rest of the proof, we again use the same useful trick. Okay, so recall our construction for the quotient complete or transitive Latin square graphs from groups. We just add the information that H subgroup of gamma L1 P to D is either of the groups described in proposition 3, since these are the possible subgroups of general semilinear group of degree 1. Also, the projection of G0 onto S3 is either generated by X or generated by XY, where X and Y act on the vectors in this manner. So these are significant in the following theorem from the 2018 paper. The result states that G0 must satisfy these conditions in a table. The first column gives the subgroup G0. The second column gives the projection H of G onto GL of U. In the third column, we have conditions on cosets. And the fourth column indicates that the entry here must be transitive on the non-zero vectors. So to list the possible G in the pairs gamma G, where gamma is G are transitive in G quotient complete, we need to identify specifically those groups G0 whose projection H is a subgroup of the gamma L1 P to D. Therefore, we only need to look in this table and determine the suitable K, G, and H satisfying either of the following. For one, K is transitive for lines 1 and line 3. So in line 2, G0 is the group generated by K and GX. H is KG, and that K must be transitive. Excuse me. So with the condition that Kg cube equals K, we deduce that K must be an index 3 subgroup of Kg. So for line 2, we need a K which is transitive index 3 subgroup of transitive Kg. For line 4, we need K which is an index 2 subgroup of the transitive KH. And for line 5, we need a K, an index 2 subgroup of KH, and KH itself is an index 3 transitive subgroup of KGH. Observe that for number 1, we know the possible K we want. These are precisely those transitive subgroups described in proposition 3. So our problem is reduced to finding transitive index 3 subgroups and index 2 subgroups for each transitive subgroup X of gamma L1 P to D. So we have the following lemma just to describe the subgroups of gamma L1 P to the D. Suppose M and N are subgroups with standard parameters CES and C prime, E prime, S prime. Here are some properties. The order of M is D times P to the D minus 1 over CS. N is a subgroup of M if and only if these conditions are satisfied. And the index of N in M is C prime, S prime over CS. So as a corollary, we are able to describe the index 2 and 3 subgroups by imposing conditions on the standard parameters. So if C prime, E prime, S prime, and CES are the standard parameters of M and X respectively, then M is a subgroup of X if and only if C prime equals 2C and S prime equals S, or C prime equals C and S prime equals 2S. We have similar conditions for an index 3 subgroup. So using these results and applying Fulser's criteria for subgroups of gamma L1 P to D, we obtain an explicit list of the possible index 2 subgroups of the transitive subgroup X with necessary and sufficient conditions on CES as well as P and D. So if X is the subgroup generated by omega tau S, then the index 2 subgroup M is one of the following subgroups listed. And if a subgroup M is one of these forms such that the conditions are satisfied, then M is an index 2 subgroup of X. So conditions in this table are deduced from the Fulser's criteria for subgroups, conditions capital F1 to F3 mentioned before. And then similarly, using proposition 3, which gives equivalent conditions to Fulser's criteria for transitive subgroups, which are the conditions small f1 to small f5, we can deduce the possible index 3 transitive subgroups N of X. So with propositions 7 and 8, we are able to get a list of possible K to describe G0, and in essence give a more explicit description for possible automorphism group G. So for K transitive for lines 1 and 3 in the table for G0, possible K are those in proposition 3. If we need K transitive index 3 subgroup of transitive KG, so KG is either of the two given in proposition 3 and K is as in proposition 8. For K index 2 subgroup transitive KH for line 4, KH as in proposition 3, and K as in proposition 7. Lastly, for K index 2 subgroup of KH and KH transitive index 3 subgroup of transitive KGH for line 5 in a table for G0. So we choose KGH to be transitive as in proposition 3, KH as in proposition 8, and K as in proposition 7. Okay, so for some examples, let's consider the case where D equals 1. Then the general semilinear group of degree 1 in this case would be generated by omega and tau. But the Frobenius automorphism over the finite field of just P elements is the identity. So gamma L1P is just the subgroup generated by the primitive element omega in CP star. So we can use our results to identify the possible K satisfying the conditions for G0 in the table in theorem 4. So the only transitive subgroup of gamma L1P is itself. So for lines 1 and 3, we can take K to be gamma L1P itself. And note that there does not exist an index 3 transitive subgroup of gamma L1P. So there are no groups satisfying lines 2 and 5. In line 4, we can take KH to be gamma L1P, where K is the subgroup generated by omega squared, which is an index 2 subgroup according to proposition 7 with a condition that P is odd. If we are able to express G0 in this manner, so we have the tools to identify the conditions by which gamma is G quotient complete with a specific number K of non-trivial complete G normal quotients. So this is from a theorem from the 2018 paper of Dr. Amara. So as our examples, using the said result from the 2018 paper, gamma, the only G arc transitive and G quotient complete Latin square graph with exactly one non-trivial complete G normal quotient, or K equals 1, is the Latin square graph of C3. And G0 is one of the listed groups in the previous table. So as an example, let gamma be the Latin square graph of C3 and G be the corresponding group such that the group of translations by the vectors from V1, this is V1, is a normal subgroup of G, and G0 is the group described in line 1 from the previous table. So this is our Latin square graph of C3. We can check that this is a G arc transitive since G0 is transitive on the neighbors of the 0 vertex. And this graph is G quotient complete with exactly one non-trivial complete G normal quotient. And this corresponds to the normal subgroup PV1. So we have this normal quotient. For example, if we apply the translation under V1 to 0, 0, so we get the orbit 0, 0, 0, 1, 1, 2, and 2, 2, 1. Okay, and this is represented. This orbit is represented as a single vertex in the normal quotient here. Okay, and then these are the other orbits. So the normal quotient corresponding to TV1 is this is non-trivial and complete. And then on the other hand, the only G arc transitive and G quotient complete Latin square graphs with K equals 2 are those Latin square graphs of CP where P is congruent to 1 mod 3. And G0 is the group described in line 1 from the previous table. So for example, let P be 7. So gamma is the Latin square graph of C7. And And we have the translations under V2 and V4 are normal in G, and G0 is C7 star times that were generated by X. Yeah. This figure shows the Latin square graph of, so this is GR transitive, since G0 is transitive on the neighbors of the zero vertex. And then G is quotient complete with exactly two non-trivial complete G normal quotients corresponding to TV2 and T sub V4. For example, applying vectors V2 to 0, 0, 0, we get, so 0, 0, 0, we get 1, 2, 3, 2, 4, 6, 3, 6, 2, 4, 1, 5, 5, 1, 3, and 6, 5, 4. So this forms an orbit, which in the normal quotient is a single vertex. And then if we apply to the all other vertices, we get this normal quotient corresponding to T sub V2. So we have a complete graph of 7 vertices. And similarly, translations under V4 give rise to orbits which form the normal quotient gamma sub T V4. So these are clearly non-trivial and complete. Okay, so that some related problems. One may try to find quotient complete or transitive Latin square graphs from Latin squares which are not multiplication tables of groups. One may try to give an explicit list of groups from the families on transitive finite linear groups associated with the quotient complete or transitive Latin square graphs, but that is aside from the family of subgroups of gamma L1 P to the D, which we considered. And then all quotient complete are transitive graphs with the number k of non-trivial complete normal quotient is at least 3 have been completely classified. However, for the case k equals 1 or k equals 2, only some infinite families or examples are known, including the subfamilies of Latin square graphs as discussed. So a still open problem is to classify these graphs with k equals 1 or k equals 2, or at least find other infinite families of quotient complete or transitive graphs with k equals 1 or k equals 2. And lastly, as part of the analysis of family of arc-transitive diameter 2 graphs, one may try to determine which quotient complete arc-transitive graphs with k equals 3 have diameter 2. So here are our references. Thank you for listening. That ends our presentation. Thank you.
Thank you very much, Homer. Let us all give Homer a round of applause. Thank you. Thank you, Homer. Okay, so the floor is now open for questions from the audience. So just feel free to unmute yourself, or you can type your question. You can also raise your hand, or just feel free to. Any question?
Homer, good afternoon. Thank you sa presentation. So, question po lang doon sa presentation mo. So, tama ba ang intindi ko na yung you needed to look at the subgroups of gamma L1 P to the D because ito yung lumalabas na kailangan tignan from the paper ni Amara noong 2018. Tama ba? Ito yung kailangan yung makalap ng transitive subgroups para magamit yung results ng 2018. Is that a correct assessment or?
Ano po, this is only a portion of the of my thesis. We chose gamma L1 P to the D to fill in the gaps from the from the different paper, which classifies quotient complete arc transitive graphs with the number k, non-trivial complete normal quotient graphs greater than or equal to 3. So yun po yung quotient complete arc transitive graphs. So not necessarily Latin square graphs with k greater than or equal to 3. Yun po may gap siya sa under gamma L1 p to the d. So kaya po nag um, nag-analyze ng subgroups ng gamma L1 p to the d. And then at the same time, pinili na rin po na gamma L1 p to the d yung family ng transitive finite linear groups na para i-list yung explicit list para makapagbigay ng explicit list of groups associated with quotient complete or transitive Latin square graphs naman. So, is that clear po ba? Sorry.
I think so. Okay lang. Tapos ang tanong ko, yung so medyo hindi ako familiar dito sa topic na to, no? So di ba parang from the original graph, nakakuha ka ng ano yung term doon, yung quotient, yung mas maliit na graph, no? From so possible naman, di ba, na magkaroon ng magkaibang graph pero ma-reduce to the same normal, ano ba ang tamang term, normal quotient graph. So for example, yung kanina yung from the yung mukhang finite geometry ba yun? Nasaan na yun? Yung C3 ata yun kanina. Tapos nare-reduce mo to tapos nare-reduce siya to ano yon, to yan triangle. Hindi unique, hindi to one-to-one correspondence. So pwedeng may ibang graph na magsisimula na gamma that will reduce to the same normal quotient pa ang term. Sorry, I'm not very possible yon.
Apo, hindi po ano siya.
Hindi siya unique. Okay.
Unique.
Tapos kaya tinitingnan yung normal quotient kasi from the original graph, yung properties na i-inherit, tama ba doon sa normal quotient?
Apo.
Meron bang nakakuha information na baliktad from the given yung ito yung alam sa normal quotient na graph, may ma-reduce ka ba doon sa original na graph or something or wala naman?
So na-inherit po yung vertex transitivity tsaka yung arc transitivity nung original graph, and then reduce to a simpler structure na i-observe. So yung mas maliit na structure na normal quotient, so it is also vertex transitive and arc transitive. Pero if we start from that po, parang parang yung reverse niya, we will have to find specific conditions para makuha pa rin yung ano. So like dun po sa normal quotient reduction na ginagawa in sa a family ng arc transitive diameter 2 graphs. So under taking normal quotient graphs po, so parang lumiliit yung structure and then may makukuha na either quotient complete or magiging trivial yung mga mas maliliit na normal quotient. So yun po, kaya ino-observe natin yung mga quotient complete graph, parang siya yung basic graph nung family ng arc transitive diameter 2 graphs.
Okay, thank you very much, Homer.
Thank you for the question. Are there other questions from the audience? Okay, so if there are no more questions, let us again give Mr. Homer de Vera a warm round of virtual applause. Thank you very much. Okay, so next week, December 20, will be the 6th and final webinar for the semester, and we will be hearing speakers from the Modeling and Applications Academic Group and the MFAS, or Mathematical Finance and Actuarial Science. Okay, so until next week, thank you very much for attending, and again, thank you to the speakers. See you then. Goodbye.